displaced in the positive direction, and this will be displaced in the negative direction. Now there's a device that we can use to measure waves called a cathode ray oscilloscope. The position of a particle in the wave Today we're going to be talking about graphing waves. We've talked previously about some of the different properties of a wave, and so it turns out that some of them look pretty cool when you decide to graph them. So we'll start off with what's put on the x-axis. Now we can graph things in a number of different ways, which means that the x-axis can be mapped to a number of different properties of the wave. Usually we use it for time, so we measure how a particular part of the wave varies over time. Makes sense, right? So sometimes it's used as a spatial dimension, that is, to show sort of what the wave looks like at a fixed point in time, rather than showing how the wave varies at a fixed point in space. So we can either show how a particular part of the wave changes over time, or we can show what the entire wave looks like at a particular point in time. Now the y-axis of the graph is usually used for the displacement of the particles. We know that in a wave, the particles get displaced, they vibrate back and forth, and so on the y-axis we show how far it's vibrated. So this will be displaced in the positive direction, and this will be displaced in the negative direction. So for transverse waves, this means that the graph will look a bit like the transverse wave. So the transverse waves are the ones that move up and down as they go across, and we can see that if we graph their displacement, it will also go up and down as the graph moves across. For longitudinal waves, the displacement is parallel, but we still graph it like this. It just means that instead of being up and down, it'll be in the same direction as the wave or in the opposite direction as the wave. So essentially we can use a graph to transform a longitudinal wave into a transverse wave. Now suppose we're plotting against position. So the x-axis measures how far across the wave itself has moved. In this case, we need to keep time fixed. So essentially what we're getting is a snapshot or a freeze frame of exactly what the wave looks like at a particular point in time. So we can think about this as a sort of still photograph, like we can see over here. So this type of graph is useful for looking at how the graph looks like overall. It's good for getting a big overview of what the entire wave's state is at a particular point in time. And so if we can measure certain properties of this graph, we can learn certain things about the wave. In particular, it's possible to measure the wavelength of the wave. If we have a freeze frame of a wave, then all we need to do is measure the distance between two of the repeated patterns. So it's going to be the interval on the x-axis between two crests, or between two troughs, for example. So the frequency can be calculated as long as we know the wave's speed. We can't really capture that with a still photograph, but if we know for other reasons what speed the wave is going at, then if we know its wavelength, we can calculate its frequency, or its period. So that's graphing against position. What was the other thing that we could graph against? Time. So in this case, we're measuring the position of a particle in the wave at a fixed point of the wave. So essentially we take out one bit of the wave. We can see that we have a wave moving to the right over here. But if we want to graph a position over time, then we need to pick just one particle in the middle and draw a graph of how it moves. So we can see that it's going to be moving up and then down over time. So this isn't exactly the same as graphing over position, because we don't see the entire shape of the wave as it moves from left to right. What we do see is the movement of how the individual particles of the wave move, which can also be useful. So the graph will represent the motion of a single particle and not of the wave as a whole. It'll show how the wave changes over time, which means that we can measure certain properties of the wave related to time. Can you think of any properties like that? So here we have a graph of the path of a particle's motion over time. We can see that it's moving up and then down and then up and then down. And so it turns out that we can use this sort of wave to figure out the period of a particle as it moves up and down. Because the x-axis is time, the distance between two crests will be the time that it takes for a single particle to move all the way down and then all the way back. And that's our definition of period. So because the x-axis is used to measure time, we can measure a distance on the x-axis to figure out a time in seconds, which will be the period of the wave. And of course, the frequency, we can just use this equation to find, f equals 1 on t. So what this will give you is how many wavelengths pass through 1 second. So if we have a time interval of 1 second over here, then the frequency will be the number of total wavelengths in that interval. Make sense? Our fixed point is the point at which we're measuring the wave. So the number of wavelengths that we get in 1 second shows how frequently the crests of the wave are passing through that point. If we know its speed, then we can find its wavelength. And if we know its wavelength, we can find its speed simply with this equation, v equals f lambda. Now there's a device that we can use to measure waves called a cathode ray oscilloscope. The screen of such an oscilloscope looks something like this. And what this does, it shows how an electrical signal changes over time. How do we apply this to waves? Well, we simply translate the wave into an electrical wave. Because remember, we can change the form of energy that the wave is transmitting. The cathode ray oscilloscope, or the CRO, tends to display the intensity of the wave over time. So what we need to do is find a way that we can translate the intensity of sound energy to intensity of electrical energy. And it turns out there's a device that's perfect for that, and it is called, of course, a microphone. So if we connect a microphone to a cathode ray tube, then that will turn sound waves into electrical waves, and the cathode ray oscilloscope will be able to tell us things like the period or the frequency or the amplitude of the sound wave. Right, so that's the end of the theory. Now we can go on to some questions to make sure you understand how to draw and interpret these graphs.